Hey everyone, welcome back to Topical Bytes. In this topic, we are going to learn the ones and twos complement. In our last topic, we learned about the binary system, where you use binary words and bits to represent decimal numbers. However, in that last topic, we have not seen negative numbers. So ones and twos complement is used if you want to represent negative numbers or if you need to have negative numbers in your count. If you don't require negative numbers, then you don't need the ones and twos complements. Or you can also use ones and twos complements just in case you need negative numbers in the future. So let's take a look at how ones and twos complement work. First, let's take a look at the ones complement. To do this, let's take a decimal number. Let's take an example of positive 5. In the binary system, we will represent positive 5 as 0101. In the ones complement, if it's a positive number, there is no need to change anything and is equivalent to its binary number or binary word, which is 0101. Now let's find negative 5. In the binary system, you do not have a representation for negative 5, so therefore this is not available. In the ones complement, if you want to find the negative number, then the first step will be to find a positive equivalent. In this case, we have already found a positive equivalent for positive 5, which is 0101. Once you have found a positive equivalent of positive 5, then all you need to do is inverse each of these bits. How do you inverse each of these bits? If it's a 0, it will become a 1. If it's a 1, it will become a 0. If it's a 0, it will become a 1. If it's a 1, it will become a 0. And this is how you find the negative of the positive number. Hence, negative 5 is represented by 1010 in the ones complement. If you are given a number in a ones complement that starts with a 0, for example 0110, then this would be a positive number because it starts with a 0. Then in the binary system, this would also be 0110. Remember that positive numbers can be represented in the binary system, and then you can find this in a decimal system, which is positive 6. Now, if in a case where you are given a ones complement number that starts with a 1, for example 1011, then how would you do this? First of all, you need to find the positive equivalent of the ones complement. In this case, I will have to inverse this number. So 1 becomes 0, 0 becomes 1, 1 becomes 0, and finally 1 becomes 0. Then I have found the positive equivalent for this 1011. 0100 is equivalent to 0100 in the binary system, and 0100 is equivalent to positive 4 in the decimal system. Because I start with a 1 in the ones complement, this tells me that this number in the decimal system is a negative, and it is equivalent of the positive number, which is now negative 4. Therefore, 1011 represents negative 4 in the decimal system. And that's how you convert between the decimal to the ones complement and ones complement to the decimal system. So after converting all the decimal systems to the ones complement number, you would have the number line as shown. Again, you can see that all the positive numbers here will start with the most significant bit of zeros. Whereas in the negative number region, all of these ones complement number will start with a 1. You can try any of this. For example, 4. If you inverse each of these bits, you will get this negative number equivalent. You can also try taking, for example, one number from the negative number and try to work out if you can get back the negative 3. So how do you do that? Remember that when you see the most significant bit is a 1, you need to find its positive equivalent. To do that, you simply just have to inverse. Now there is one binary word that is missing from this ones complement number system. Let's try from here. You have 1000. If you increase by 1 in the binary number, you would have -6. And if you increase by 1, you get 95, and so on up to 1110. However, 1111 is missing. So let's discuss the disadvantage of this ones complement system. What does 1111 represent? In order to understand this, let's take a look at the first bit. The first bit is 1. which tells us that it is a negative number. So now we have to find its positive equivalent. To find the positive equivalent, we will just have to inverse all of this. So 1 becomes a 0, 1 becomes a 0, and so on, and I will get 4 zeros. 4 zeros in a binary system would represent 0 in the decimal system. Hence, 1111 in the ones complement system represent negative 0 in the decimal system. However, there is no such thing as negative 0 or positive 0. So therefore, if we look back at this number line, 1111 actually also represents 0. And this is the disadvantage of the ones complement system because you have two binary words to represent one decimal number 0. Hence, it's a waste of a binary word. The two's complement actually offsets this disadvantage. So let's take a look at how the two's complement work. Let's try again the decimal value of positive 5. In the binary system, positive 5 is represented by 0101. In the ones complement, we have the 0101 as well because positive number has no difference between the binary and ones complement. In the two's complement, the positive number also does not have any difference and therefore it is also represented by 0101. Now let's find the negative 5. In the binary system, remember there is no negative number representation, so therefore this is not available. In the two's complement, you take the inverse of this one's complement and you plus a 1. So in other words, you have to inverse your positive number and then you plus a 1. In the two's complement, this will be represented by 1011. So let's try reverse engineering. Let's say we have 1110 in the two's complement. Likewise, when you see the first bit is a 1, this tells us that this would be a negative number in the decimal system. So how do we convert back to the ones complement? First, you need to subtract a 1. When you subtract a 1 from this 1110, you will get a 1101. So this is the 1101 in the ones complement already. Now 1101 we need to inverse to find its positive equivalent. So we would get 0010. 0010 in the binary system is also 0010. There is no change. Remember, positive number is equivalent. And 0010 is represented by positive 2 in the decimal system. So remember, the first step will be to subtract 1. The second step will be to do your inversion. And then you find its positive equivalent number, which is now positive 2, which means that 1110 equals to negative 2 in a two's complement system. And then you have the number line as shown. Apologies for the typo, this should be 0000. What we just did, remember, 1110 tells us that it is negative 2. You can try another example, for example, negative 7. All you have to do is first minus 1 to get 1000. After subtracting 1, inversing this 1000, you will get 0111. And you notice that 0111 is equals to a positive number 7. And that's how we get 1001 representing negative 7 in the two's complement system. Likewise, all positive numbers in the two's complement starts with zeros, and all negative numbers in the two's complements all starts with ones. Now again, there's one binary word that's missing from here. And what is that? That is 1000. You notice that there is 1001, but there's no 1000. So what does 1000 represent? Now let's go back up to our analysis. In this case, we have the two's complement number of 1000. And we do know that this represents some negative number in the decimal system because it starts with a 1. Because it starts with a 1, it must be some form of negative. So how do we find its positive equivalent? First, we subtract 1. By subtracting 1, we would get 0111. And this would be similar to that in the ones complement. Remember, from ones complement to two's complement, you plus a 1 if it's negative. So in this case, the ones complement now is 0111. To do that, To find the positive equivalent, then now you have to re-inverse this number. When you re-inverse this number, you get a 1, 0, 0, 0. In the binary system, this will be 1, 0, 0, 0. And in the decimal system, 1, 0, 0, 0 represents 8. Hence, the 2's complement 1, 0, 0, 0 represents negative 8 in this system. If we go back to the number line, 1, 0, 0, 0 represents negative 8. And you can see that now each binary word represents a different decimal number. Unlike the 1's complement, whereby you have 2 binary words to represent the number 0, in this case we have 16 different binary words to represent all different numbers, whether positive or negative. You have total of 16 different representations. If you have a positive 4 in the binary system, it will be represented by 0, 1, 0, 0. In the 1's complement, remember there are no differences, so it's still 0, 1, 0, 0. Likewise, in the 2's complement, all positive numbers and binary numbers and 1's complement are exactly the same, so it's still 0, 1, 0, 0. For 94, we do not have a representation in the binary system. In the 1's complement is just simply the inverse of this, so I get 1, 0, 1, 1. And the 2's complement is the plus 1 from the 1's complement, so therefore when I plus 1, I will get 1, 1, 0, 0. Positive 8 in the binary system is represented by 1, 0, 0, 0. There is no positive 8 in the 1's complement system because it only goes up to positive 7. In the 2's complement, we also don't have the positive 8 value. The negative 8 is not represented in the binary system. The 1's complement also does not represent the negative 8s. In the 2's complement, the negative 8 is represented by 1, 0, 0, 0. And 0 in the binary system is represented by 0, 0, 0, 0. 1's complement represents 0 in two ways, which is 0, 0, 0, 0 or 1, 1, 1, 1. And in the 2's complement, 0 is represented by 0, 0, 0, 0. So if you are in the 1's complement, in order to find the negative equivalent, the first step will be to inverse, and the second step will be to find its positive equivalent. If you are given a negative number in the 2's complements, the first step will be to subtract 1, second step is to inverse, and the third step is to find its positive equivalent, and then you get the negative of that equivalent. And that's 1's complement and 2's complement system. Thanks for watching. Don't forget to like and subscribe to get notifications on the next Topical Bytes video.